Yes, yes, folks. So let's start with our virtual RFCs We Love meetup. Thanks everyone for attending. Thanks Russ for waking up early and being here for the call. Thank you.
It's not that early for me, but it's cool.
Good. So for the folks who are attending our meetup for the first time, since the lockdowns, we have moved to an online setup, and this is our second fully online meeting. Before that, we used to meet physically, mostly in Bangalore and once in Kolkata. So this is our 15th meetup overall since we have been doing this. And this has been organized by IIESOC, which is India Internet Engineering Society, which was established around 2017. And we have been organizing this meetup as well as a pre-ITF meetup called Connections since 2017. So all this information you will be able to find on our website, etc. So before we start, we usually have some new folks. So we wanted to know how many people who are new to this. So could you just go to menti.com and enter the code that you see on the top, that is 306638, and then you will be able to enter. So we would like to know what's the makeup of the room today, like how many people who are uh, here for the first time. We usually have that. And we welcome new participant, of course. We wanted to see how many people who've been with us for a long time. So we see around two people who have attended more than 10 events, two people who are new, some around 2 to 5. That's pretty good. I'll leave this slide for 1 more minute. Oh, good backup. Yeah, you can just log into your mobile anywhere, and this will be a simple browser, and you will be able to enter the information. And even when I go forward, you will be able to still enter this information. So feel free to add this. Moving on. We usually used to have voice introductions, and we know that that's going to take quite a bit of time now since the number of people have been increasing. So we thought let's try it using the Menti mechanism, so folks can just enter uh, on the web page just who they are, where do they work, what area they are interested in, any information that they would like to introduce, and all the information would get displayed on the screen as well as gets collected in our proceeding. So don't be shy. Just give a very small few words introduction. I'm Dhruv. I work for Huawei. I've been involved in ITF for a couple of years. I run a PC working group as a co-chair in ITF. I'm also in the routing directorate, etc. I'm interested mostly in the routing area with path computation and traffic engineering. So things like that. Please feel free to add and introduce yourself. So we do see that we have a good mix of people in today's call with various interests, and we have a good set of topics as well. So I hope today would be a interesting day. I still have a few minutes as a part of our introduction, so I'll give you guys a little bit more time. Wow, welcome. We have a member from Sudan, so that's very good that you can join this call.
Yeah, yeah. Also see Shraddha. Hi, Shraddha.
Yeah, it's good to see folks with very different set of interests, some from faculty, some working in our vendors. Uh, we should work with more service providers. That's something that we have struggled. We have had some participants from Reliance, but after that, that has not been there. So that's one area that we continue to see that we don't have participation yet. So maybe working with SANOG or something is something that we are looking forward to in future, so that we can get participation from that community as well. So thank you, folks. Thanks for introducing yourself. Keep adding. This information will get collected even when I've moved on. So we know that ITF 108 is coming. It's going to happen on July 27 to 31 for 5 days, and it will be a fully online meeting. From India time, it would start at around 4:30 p.m. In India, and would be running for an approximately 5 hours per day. This working group and the research group sessions would be around 50 or 100 minutes. Those are the only two time slots that the will be given. The early bird registration are at the cost of rupees USD 230, so it's a bit high, and it needs to be given 26 June. So this is something which is being discussed even on the ITF mailing list right now. There is some contentions whether earlier remote participation was free and many people from our community were able to participate, and this fees could be a dampener. So there is two things. Further discussions is actually happening on the list, so we don't know what's the final decision there. But one thing is that we have a fee waiver program for around 30 for around 100 folks. It would be lottery based if the number of requests is more than 100. So use this opportunity, especially if you have difficulty from support from work or you are self-sponsored. There is a fee waiver program, so don't be disheartened by looking at the 230 USD fees for the remote participation. And this is something that will continue to be discussed. So if you are on the ITF mailing list and want to give feedback, this would be a good time to give a feedback of how this fees impact you and where you were able to participate earlier, but now it might be a little bit difficult. So please be vocal. Then only our community needs can also be handled. But if your work uh, can sponsor this, please ask for support, and that would be our first preference. Only for people where that is not a possibility, the fee waiver program can be utilized. So I wanted to pass this information to folks here who are not on the ITF list. Note that the YouTube video, the meeting material, even the Jabber rooms, those things would continue to be there for offline viewing. So you can still participate even if the fee waiver did not work and you are not able to pay. So reach out to me, reach out to other people if you need any support during this ITF 108 participation. Uh, who we are, as I said, we were IESOC. You can find more information about us through these channels. We have ITF mailing list, which is hosted by ITF as ITF Community India. So that's our main mailing list. So please join if you are not already there. Apart from that, you can find information on our website. You can email us, Twitter. Our WhatsApp group is also quite active, so consider joining. I put the link there, and I will be sharing the material on the website anyway if you need this link information. So let's start with our agenda for the day. We have data center routing by Russ White, how India censors the web by Gurshibad Grover, and decreasing access time to DNS root servers by running one as loopback. So talking about a particular RFC 7706 by Swapnil Patnekar. So we have a very good set of topics, diverse topics. So hope you will find this quite interesting. So let's start with our first topic, which is DC routing. Russ White, who is the co-chair of ITF, I2RS, and Babel Working Group, is here. He has a lot of experience in designing, deploying large-scale networks. He has been involved with, in fact, development of Cisco's CCDE and CCAR programs, lots of patents, and we can learn a lot from him. So thanks, Russ, for participating and help joining us for the first time in our meetups. He's also interesting co-hosts two of our favorite networking podcast, The Hedge and The History of Networking. I put the link for both of these podcast page on our blog where we are introducing. So if you have not heard this, do give it a try. It's really interesting, and you will hear a lot of interesting stuff rightly from the mouth of the people who are doing some interesting work, not just at an ITF, but outside in the industry as well. So off to Russ. I'll stop sharing and I'll ask Russ to share his so that we can start with our first presentation.
So while I'm getting set to share here, I will say that The Hedge and History of Networking are both rather open format. And if anyone on the call here has a topic that they would like to talk about or some history, like we do regional perspectives, the history of the internet in particular regions, the origins of different IXPs, organizations. It's not just for technologies. I'm perfectly willing if you shoot me an email to set up some time. We normally record on Zoom. It's very simple to do a recording. And so, or if you have something about networking you'd like to talk about that you think would be an interesting topic for the hedge, that's great as well. Also, as far as certifications go, I'm actually trying to work on a new certification. I've been very quiet about this, but I'm trying to build a team to work on a new certification if anybody's interested in that. It's not really a certification, it's more of a challenge. There will be a Packet Pushers podcast recorded on this, releasing sometime in July. But if you're interested in helping out with an effort in building something that's more open and industry-based, more open organization and industry-based in the realm of quote-unquote certifications, please feel free to PM me on LinkedIn, or you can find my email address on LinkedIn as well. It's very easy to find my email address. So let's talk about link state on data center fabrics. So routing on data center fabrics has traditionally been, the standard has always been, and by the way, if you have questions, feel free to interrupt me. I do these things very interactively, and I am perfectly happy to answer questions along the way. It's going to be hard for me to watch the chat window. So maybe if somebody puts something in the chat window or just say something, I don't know, just so I can keep up with any questions that have been asked other than through audio. So anyway, so BGP has been the standard for DC fabrics ever since Petalupkov put out his draft about the way Facebook was using BGP on their data center fabric. And so Ivan Pepiniak often likes to say, why do you use BGP on your data center fabric? Because, hey, everyone else does it, and because RFC blah, blah, blah says to do it that way. So let's talk about, though, there's this huge effort in the IETF, apparently, to do link state on data center fabrics. For instance, draft IETF LSR dynamic flooding, which is Tony Lee and a bunch of people have been working on this. LSR area proxy, which is Tony P, Tony Lee, and a bunch of other people. My draft, which is DisOp flood, which is what I'll largely be talking about, other than a comparison draft with a comparison slide later with Rift. But if you're interested in how Rift or any of these others work, I do know enough about them that I just generally have blank slides. So if you want to know more about those and we have time, I think we have till 10 till the hour, well, 20 till 20 after the hour is pretty much what we're doing, or something like that, or 10 till the hour in my time, or 20 to 20 after the hour in your time. I can talk about those a bit more. I actually have done a lot of work with Rift, and I've spent a lot of time looking at and listening to Tony on these things. But the question is, why? Why are we doing this? Why are we so concerned about link state on data center fabrics if we have BGP? And BGP seems to be a perfectly valid and usable solution. Well, let's begin by just defining some terms. I'm very persnickety about my terms. If you've listened to any of my stuff in the past or read any of my stuff, you know that I use aggregation and summarization to mean separate things. And that's just because I find that clarifying my terms and really understanding what I'm saying and using technical terms is very important to clear thinking and understanding exactly what I'm talking about. By the way, I wasn't quite so persnickety about this until I started doing a PhD program. And my major professor in my PhD program is extraordinarily persnickety about terms and about the way you say things. It's not a PhD in technology, it's a PhD in philosophy. And so you get very strict concepts about these things and what they mean. So I'm going to use three terms here, and I'm going to talk about the importance of having these three different kinds of things. One is having an infrastructure underlay, which the infrastructure underlay is providing me essential basic connectivity. So it allows me to build my tunnel tail and head ends. And then there's an infrastructure overlay, which gives me my reachability through the tunnels I built on top of the underlay. Then I have what I call an application overlay. Now, this could be orchestration. This could be Kubernetes. This could be NSXT. This could be lots of different things that you're using to build application routing on top of your infrastructure. Now, one thing that you'll note here is not all networks have infrastructure overlays. When I work for LinkedIn, the LinkedIn network does not have an infrastructure overlay. There's no EVPN. There is nothing but the infrastructure underlay, which provides pure IP and MPLS connectivity, and really just IP in the case of LinkedIn, and an application overlay, which is provided by the applications sitting on top of the infrastructure underlay. So it's perfectly valid to have a pure layer 3 infrastructure underlay with no EVPN overlay. It just depends on your requirements, but I still distinguish these as 3 separate things. So given that terminology, why not use BGP as your IGP? There are 3 reasons, and I'm going to go through each one of these reasons and try to explain them the best that I can, so that you kind of understand why BGP is not a very good IGP. First of all, it converges very slowly. I'll talk through why this is, but BGP does converge very, very slowly in IGP terms. BGP in a lot of networks, well, in the internet, Alex explained how BGP converges in just a second, so I don't want to spend a lot of time talking about the speed of convergence here. It's designed as an overlay. And again, it's designed for policy, and these two kind of go hand in hand. That the BGP is designed as an overlay policy protocol. I used to say BGP and still sometimes say that BGP is really a policy protocol, a policy distribution mechanism that happens to share reachability. Tony Lee doesn't like it when I say that. I said that on a history of networking once when Tony was with me doing a history of BGP. And he was not very happy with my description of BGP, so that's okay. So let's talk about why BGP converges very slowly. And essentially it comes down to this concept. It's called hunt. This is something that was kind of discovered in general in the internet maybe 15 years ago, but it was pinned down and explained by a guy named Daniel Walton, who doesn't really work in routing anymore, but he was absolutely brilliant when it came to understanding things. And he did a lot of the work of making BGP converge much, much faster in understanding how to do peer groups and how to resolve hunt, and also how to resolve what we call BGP wedgies. So in this network, let's just take that I am trying to get P to have reachability information or have 110://64 as a reachable destination. Okay, so that is my goal, is I want to get the reachability information about 110://64 to router P, so that devices out here past router P can reach that destination. Now, if I have cut off everything except AS path length, and I assume every router in this network is its own AS, then which path is BGP going to choose? It's going to choose, given no local pref, given no med, given no other tiebreakers, because by the way, those are tiebreakers. Actually, AS path is also a tiebreaker, but given that AS path is the only tiebreaker used, it's going to use this path right here through G, because that's the shortest AS path, right? Now, let's say that we have the absolute worst case scenario happen, which is for BGP and all distance vector protocols. This is the absolute worst case scenario for routing convergence, which is the link itself, the reachable destination itself, falls off the network. It's no longer reachable. So when this happens, what we can do is we can look at timing-wise what's going to happen in a path state vector protocol or a path vector protocol. A at T1 is going, let's just call T1 the first moment in time, T2 the second moment in time, T3, etc. So this link falls off the network. At T1, A is going to send a withdrawal to G. A is going to send a withdrawal to B, to C, and to D. So those are my withdrawals. At T2, G is going to send a withdrawal to P, and B is going to send a withdrawal to M, C to F, and D to E. At T2, P receives this withdrawal and says, my best path is now gone. So what I'm going to do is I'm going to flip to my second best path. What is my second best path? It's through M, because that's my second shortest, or my not quite the shortest AS path. So at T2, P is going to flip to M as its best path. Now, at T3, M is going to send a withdrawal to P, F is going to send a withdraw to K, and E is going to send a withdraw to H. At T3 then, P now says, oh, look, my best path is gone. I need to flip to my next best path, which is going to be through K. At T4, K sends a withdraw to P, H sends a withdraw to N. So at T4, P says, oh, look, my best path through K is now gone. I need to flip to the only remaining path I have left, which is through N. At T5, N sends a withdraw to P, and P finally removes the 110::/64 route from its routing table. Now, it's not quite this simple, of course. There are all sorts of updates and other garbage that goes on here. I'm just simplifying it to the very simplest mechanism. So what is happening here is BGP is going to hunt. It's going to choose. It's going to start with its shortest AS path, and it's going to try every possible AS path between its shortest path and its longest path. The amount of time required to hunt across each one of those paths is MRAI, min route advertisement interval. I can actually cut back on the convergence speed in BGP by setting my MRAI to 0. What this does, however, is it up to or makes worse than quadruples or above the number of updates and withdraws in the network if I'm actually looking at the way the network converges. So the MRAI is a strict trade-off or straight trade-off between speed of convergence and number of updates and amount of processing in the network. So this is effectively how BGP converges. So I always say to know how long BGP is going to take to converge, all I do is I take my shortest AS path, I subtract it from my longest AS path, and I multiply this by the MRAI. That's effectively how fast BGP converges. Now, if I look at a network like this is a small butterfly fabric, this is a full-out butterfly fabric using 4-port devices. What I will see is if something falls off the network right here, I have all of these alternate paths. I have tons and tons of alternate paths going through this network. And BGP wants to hunt over all of those paths. And I can actually figure out, actually on a large scale network, on a truly large scale network, what I've seen is if I put 2,600 or so routers on a butterfly fabric of this kind, so there are 32 planes rather than 4 planes, and et cetera, et cetera. It's a much larger network than this. And I just go all out and make every router in this network its own AS. And I would draw, say, 120K routes from the edge. BGP will never converge. It dies. It's done. It just flat never converges. There are a lot of tips and tricks that I can do to make BGP converge in these large-scale networks. One of which is I can go down here. Well, again, what I'm trying to do is I'm trying to get rid of the hunt. So if I just think about it in terms of getting rid of the hunt, how do I make BGP converge faster? The things I can do is I can cut out as many paths as possible. So for instance, I have paths that are valley routing, right? These valleys are potential paths, and BGP needs or wants to hunt through them. So one thing I can do is I can go down here and I can set up an AS path filter that is $, which says in regex, do not advertise anything that is not locally originated, because this eliminates all routes that have an AS path greater than 0. Since the local AS is added to the AS path when I'm advertising the route to my eBGP peer, this allows me to say, don't advertise anything that's not locally originated. Other things I can do is I can put all 4 of these routers in the same AS. And since BGP will automatically reject any route it receives within its own AS, when a route comes up, pushes across, and comes back, I will simply not accept the route again. So that reduces the number of paths that I have to hunt across. But this mess of making BGP converge faster still doesn't make it extremely fast. Still, again, looking at a 25 or 2,600 router network, converging across 120,000 routes in the absolute worst situation, which is withdrawing all 120,000 routes at once. The best I'm going to get is about 1 minute convergence time. And that's messing with everything I can think of messing with, cutting the MRI to zero, accepting the greater number of updates, all this other stuff. That's about the best I can get. So that's one problem I run into with BGP as an underlay, as an IGP, is that BGP doesn't converge very quickly. Another thing I run into is that BGP was really designed as an overlay protocol. There's this old feature in iOS and GNOS and all these operating systems where you could do something called BGP synchronization. So what is BGP synchronization about? BGP synchronization is the concept that if I'm running BGP between B and F, iBGP between B and F, and I'm pulling routes from A and I'm sending them to C, if what happens here is if I have some destination, say 110:/64, and I advertise that route to C, so the destination's over here at C, and I advertise it only through BGP, what's going to happen is when the traffic from G reaches F, F has a BGP route for this destination. When the traffic reaches E, if BGP is not running on E, that route doesn't exist. Therefore, the information is tanked. The packets are tanked. They're thrown away. So what BGP synchronization did was it said that you must have all the routes in your IGP that you have in BGP. So what you would do in the old days, before the routing table got really, really huge, is you would actually redistribute your BGP routes into ISIS or OSPF at your eBGP speakers to force all of the intermediate routers to have the information they need to forward traffic. Now, we don't solve this problem this way today. We solve this problem with route reflectors, right? And route reflector clients. That's how we solve this problem today. The intermediate solution, by the way, was confederations. Confeds were the original solution to solve this problem, but they turned out to be really messy as well. So route reflectors were the more recent solution to this problem. So now, yes.
Sorry, with the MPLS, can't you just tunnel the packet so that the intermediate routers wouldn't have to know each of these prefixes?
Yep, that is correct. That is the concept of a BGP free core.
What was it? BGP?
BGP free core.
Oh, yeah, BGP free.
Right, exactly. So that's how we started doing BGP free cores way back in the old days, as we would run in PLS tunnels. But that actually points out what's going on here. BGP is the overlay protocol, right? What you have to do is you have to tunnel through the underlay to get the information you need, right? So you're either building this really fancy overlay of a secondary protocol. So I have an underlay protocol, an infrastructure underlay, which is ISIS or OSPF, even in a transit provider. And then I have this overlay, which is BGP. Awesome. So yeah, so I either have to tunnel across the underlay, or I have to figure out how to get every router that's in the underlay to have the overlay routes. So this is just BGP's inherent design. It was designed to be an overlay protocol. So that means also it doesn't necessarily make a very good IGP. It doesn't really make a good underlay protocol. It's not what it's designed to do. Another thing about BGP that's interesting is that when I peer between ASs, I don't want my peering to come up automatically. It's a huge negative. In fact, a recent feature in FR routing and in BGP, in GNOS and in iOS, and there's an RFC on it now, is that you shouldn't peer unless you have policy configured. Well, that tells you like BGP peering is designed to be policy oriented, and you really shouldn't peer unless you have a policy done. So what we've done for data centers is we've actually inverted the entire concept of what BGP is designed to do. So what we've done is we've gone out and we've modified BGP to do automatic peering. We've modified the way we deploy it to turn it into fancy RIP to make it converge faster. We've done all of this stuff to make BGP into an IGP, which begs the question of why, or makes me ask the question, sorry, that's not the right term, begs the question is a logical fallacy, and seeing my philosophy is like going to just drive me nuts. I can't use the wrong terminology. Anyway, makes you ask the question, why am I trying to use this as an IGP? So another thing that comes into play here that a lot of people don't think about is just failure domains. If I make my infrastructure underlay and my infrastructure overlay a single protocol, then I have actually built a single failure domain between the underlay and the overlay. Now, there are some implementations, GNOS in particular, that runs eBGP and iBGP as separate daemons. So in that case, you're not really building the single failure domain like you might in an implementation like iOS or XR, or even FR routing, where it is an actual single daemon. All of BGP is a single daemon. So what that means is if my overlay crashes for some reason, if I have some sort of an EVPN blowup, like, I don't know, some broadcast domain failure or something in EVPN that destroys BGP in the overlay, I'm actually impacting the underlay reachability. That's a very bad thing to do. You really want your underlay and overlay to be separate failure domains. So one thing you can do here is go back to the old transit provider paradigm and use two different protocols. So they are completely separate. Now they're still going to interact. They're still going to have an interaction surface, but still it is better to have them as separate failure domains. So there is another thing here, which I'll actually talk about when I get to routing on the host. I think I have that many slides. Talk a little bit about routing on the host. In that you can talk about security as well. So this makes things a lot easier to scale. All right, yep, here's my routing on the host. Oh no, this is telemetry. All right, so other reasons to use a link state protocol. So let's say that I want to monitor the state of this entire fabric. And this is a really small fabric. It's, just a 3-stage CLO that's only 4 wide by, like a 4 wide 3-stage CLO, which by the way, 4 would be, well, actually 4 is a fine number, never mind. But if I want to monitor this and I want to be able to say, take a snapshot of this topology every 5 minutes so that I can roll back. I can say, I want to look at what the network, I see an application failure and I want to be able to recreate the network 5 minutes ago to figure out what was going on in the network. If I'm running BGP, there is absolutely no easy way that I know of to solve this problem. You can use BGP LS, but it's got to run on every device. There's just really, you could use BMP and pull the database or pull the updates as they come in and do everything separately. With a link state protocol, I can attach to any device with a in my management station, I can attach to any device and just simply consume the entire LSDB. And that gives me the whole topology within a flooding domain. Now I'm going to assume in all of my link state stuff that I'm always dealing with the single fabric being a single flooding domain or a single area. Flooding domain and ISIS, area and OSPF. Mostly what I'll be talking about is ISIS work. A lot of what I'm talking about does apply to OSPF, but I just tend to think in terms of ISIS these days. So it's just kind of native language. So another reason for using a link state protocol and separating out the overlay from the underlay is to think about how this works from a security perspective, right? Assuming that I have a virtual process sitting here on H1, some sort of VM or container, whatever it is, if that container, if that routing protocol, if the underlay routing protocol is running out to the host, and it's an IP-based protocol, if I can gain control of the underlying host operating system in some way through the VM, I can now destroy or denial of service the entire fabric. Whereas if I don't run the underlay out to the host and I only run the overlay, then in theory, the only thing a VM, and I've gotten my separations right, my microsegmentation or my segmentation correct. In theory, the only thing the VM can impact is the virtual overlay segment or the VNI that particular VM sits on. So that gives me a bit more security separation. Now, of course, security is one of those things. I always believe in descent and depth, more is better type of thing. So I consider this a plus. So let's talk about the perception versus the reality of dealing with link state protocols on data center fabrics. The perception is that link state protocols cannot scale to enough nodes. And this is all because of SPF runtime. We all know that SPF is a very, very complex and processor intensive algorithm or heuristic. It's really a heuristic, not an algorithm, but we call it an algorithm. Anyway, now, so we know that's true. Now, Dijkstra originally wrote SPF to run on a 6-bit processor and, just the formation of building the shortest path trees and everything. But we know this is a very complex, very difficult thing to run. The second thing is that we know, or we believe, the perception is that link state protocols cannot scale to enough reachable destinations. This is pure route count, right? We all know or believe that if you throw 250,000 routes or 2 million routes at a link state protocol, that it's going to fall over. It just simply cannot support that many destinations. So a third thing that we all perceive, or we think we know, is that flooding just isn't efficient enough to scale. That you just can't get 2,500 or 3,000 or 5,000 routers or intermediate systems into a single flooding domain and make it work. This is why we have area border routers and L1 and L2 routing in IS to IS and area border routers in OSPF, is because, in fact, it used to be on Cisco.com that you would see a statement that you could put no more than 50 routers in a single OSPF flooding domain or area. It turned out that that was not true. And Don Slice and I spent several years, believe it or not, correcting the documentation on Cisco Online because 50 routers is a ridiculous number. That was just, at one point, maybe with an MGS or a Cisco 2500 or something with a little 8088 class or 8080 processor, class processor in the box and 2 gig of memory or 256 meg of memory or whatever it was. 50 might have been appropriate, but that's nowhere near appropriate at this point. And it wasn't 10 years ago when we had it removed. So, but we know people say flooding can't scale. Third, another point that people make is there isn't any policy. Link state protocols just don't have policy, particularly when you're in a single flooding domain. You can't do aggregation. You can't do summarization. You can't do traffic engineering, stuff like that. It's very difficult, much more difficult to shape your traffic in a way that you want to, or you can do traffic engineering. I shouldn't say traffic engineering, but you don't have the kind of policy that you want, route filters and stuff like that. Another one is link state protocols are really hard to troubleshoot. Everybody goes out and looks at ShowISI's database and goes, oh my gosh, I don't know what to do with this information. I don't know how to work with this stuff. And finally, there aren't any good reasons to use an IGP. BGP is good enough. It works. We know it works. Awesome. Move on. So let's look at the realities of these. LS protocols for SPF runtime. Modern processors can run optimized SPF in less than 10 milliseconds. In fact, a lot of times it's less than a millisecond. There was a time when I was working on something called NotVia, which was for fast reroute. And one of the criticisms of NotVia is it added lots of SPF works. And actually constrained SPF has exactly the same criticism for traffic engineering, for MPLS traffic engineering. When you're building LSPs, you have to run a constrained SPF to build the label switch path. Well, people would say, well, you can't run SPF. You've got to run in this network. I've got to run SPF 5,000 times or 1,000 times. You can't do that. SPF runs 100 to 200 milliseconds. And so it's going to take, all this time. Well, through that process and through other processes and for other reasons, the SPF algorithm was so heavily optimized that you can now run thousands of copies or you can run SPF thousands of times in a single second. It's absolutely insane. SPF is so much more efficient than it used to be back in the old days. And we're running on really much faster processors that are multi-threaded and have all these capabilities and lots of memory. And SPF tends to be very memory bound. So having the memory to use to do things that are crazy makes SPF a lot faster. So this is total nonsense. We can run SPF very, very fast now. Link state protocols cannot scale fast enough for reachable destinations. All right. So here there is a difference between OSPF and ISIS. OSPF, because of the way OSPF structures its the packet information, it is very difficult to do what is called a partial. Let me explain what a partial is. So in link state protocols, I have two distinct pieces of information that I'm dealing with. One is my topology and one is my reachability information. People confuse them. That's why people have a hard time understanding link state and troubleshooting link state, is because they munge these two concepts together in their head. They are completely different things. One is the topology. What does the topology look like? The second is what is reachable across that topology. Now, if I look at a shortest path tree, even in OSPF, those reachable destinations are simply leaves off the tree. They are not part of the tree itself. In theory, if I lose a reachable destination, I don't need to run SPF. I can add and remove destinations. The only time I need to run SPF is if I actually drop a node or a link in the network. So this is called a partial. Now, the problem for OSPF is that OSPF, the way the things are structured, the way the LSAs are structured in older OSPF. Now, in OSPF v3, with all of the TLV-based stuff, you can actually do partials again. But in old OSPF v2, it was very difficult to do partials because when you receive an LSA, you don't know what's changed until you've actually run SPF. So it's very difficult to do a partial. ISIS, because of the way it's structured, automatically does partials. So you have modern processors, you have partial SPF, you can easily get 250,000 prefixes into ISIS or into OSPF, and it'll run. It's fine. It'll be less efficient with OSPF. You'll take up more processor time, but it's not difficult to run 250,000 to 300,000 prefixes in a link state protocol today. So this is kind of another kind of just a myth. Flooding isn't efficient enough to scale. Well, we have higher speed links and we have optimizations, which we'll talk about some of these things. There isn't any policy. This is not a bad thing. Policy should be in the overlay. If my overlay is application oriented, it's an application overlay, or if it's EVPN, it's BGP based. Therefore, that's where my policy should be. My underlay, infrastructure underlay, should only be giving me basic IP connectivity. All right, link state protocols are hard to troubleshoot. Guys, grow up. Go learn it. Sorry, I don't mean to be mean, but get over it. It's not that hard to troubleshoot. It's no harder than BGP, honestly. So no good reasons to use an IGP. I've actually already talked about this, so I'm not going to spend any time here. So let's talk about routing to the host just for a second. Let's say that I wanted to be able to run routing to my host. There's a lot of very valid reasons to run routing to the host. I have dual homing. I want to make these into a virtual lag or something like this. Awesome. So my argument would be is that I go back and this is a scale issue for a link state protocol. It's one thing to run a link state protocol on a fabric with 2,600 routers or intermediate systems, depending on your terminology, whatever you want to say. If I add 120 or 250 hosts on that to that, I have done, this is a magnitude problem. This is a scale of a magnitude larger. So I've got to think about this, right? But my argument would be is that if I'm truly running an infra underlay and an infra overlay or an application overlay or an application overlay, there is absolutely no reason for this infra underlay to be running on this host. Every advantage I get from routing on the host, I get from running the application overlay or the infra overlay on the host, not the infra underlay. So that is kind of my scale resolution there. All right. Now let's go back to optimized flooding, because this is where the drafts, the IETF drafts come in that I talked about in the very beginning, draft Lee and everything like that. There are 4 essential ways that you can solve the flooding problem, and only 4. I call this my 4 things speech. There's only 4 problems and there's only 4 solutions to every problem. It's not always true, but it's a good rule of thumb. If you haven't found 4 solutions or 4 problems, you need to keep looking because you might actually be missing some. There are cases when there's only 2 or 3. But 4 seems to be a magical number to me. All right, the first way you can do this is you can create a flood reflector, much like you would run a route reflector in BGP. And here, everyone sends their modified LSPs up to the flood reflector. And then the flood reflector refloods them to everybody, and everyone runs SPF locally. All right. There is an old paper written by some folks at Google called Jupiter Rising, and they describe a system called FirePath. FirePath is this solution. I don't know if Google still uses this today, but this is definitely something they went through doing. Another solution is a centralized calculation of reflooders. So you can have everybody send their topology to a centralized server or a controller. And this controller says, all right, you need to reflood, and you need to reflood, and you need to reflood, and you need to reflood. Nobody else needs to reflood. So it can actually centrally calculate a minimal spanning tree for flooding. That's what it's doing, is it's calculating a minimal spanning tree for flooding. If you look at all of Tony Lee's work coming out of Arista, that's what he's doing. Another way you can do it is you can do it in a way that is very topology oriented, where you can say, I know that I should need more information at my fabric layer than I do at my top of rack switches. So I'm going to increase and decrease information, flood up differently than I do down. This is essentially what Rift does. And finally, I can do something that is distributed and topology agnostic, which is what Draft Desktop Flood does. And there is a whole body of work that, if you go back and look, that is around OSPF in MAN-A. And it's called the Orca. There are a thing called Orcas. That you can go read that. That's deployed in the real world in military environments for mobile ad hoc networks to optimize flooding of OSPF in this network, or in these kinds of networks. So let's talk about Desktop Flood specifically, because that's my draft, and that's the one I kind of know the best. I do know the others. Again, I can explain them better if we have the time to do so, but let's talk about Desktop Flood first, just to give you a sense of how this works. There are two directions. Now, note that I always draw the center of the network in the center, and I have top of racks, and I have top of racks. And most people draw their networks, their data center fabrics, their clo fabrics, or spine and leaves with the spine at the top, and then they draw it with 3 down or whatever it happens to be. I don't do that because I find it a lot easier to understand how the network converges, how the routing protocol works and flooding works when I draw it flat like this. And by the way, this is the way Charlotte Clow and Benesh and everybody working on this, building these fabrics for telco networks, drew them in the first place. So I follow their, I have telco experience, so I draw them the way telco people would draw them, essentially. All right, so there are two ways of looking at the optimization. I call them forward and reverse, okay? And there's also within the router or within peering optimization as well. So forward direction, let's say that I have some destination. I always use 110::/64 as my destination, and it falls off the network. So this device right here, this intermediate system or router, modifies its LSP. Now, normally what would happen is it would flood to each one of its neighbors or peers, neighbors, and then they would reflood back. Okay? So these devices would get 4 copies of the LSP. And then these two devices would get 1 copy of the LSP. And actually they wouldn't, because it would reflood back. It would bounce and potentially get 2, just depends on how the timing works. This device would get 2 copies and these would get 4 copies. So you can kind of see how you get a lot of flooding. In the network I talked about before, which was virtualized in the 2600 router network, on each one of these devices, I was getting 40 plus copies of each LSP. And that's just a matter of timing and the way things work. The flooding load is really, really tremendous unless you do something about it. So the first thing that happens is in Desktop Flood is I look at all my 2-hop neighborhoods. So I say, who can this router reach? 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 And then I say, look, what I want to do is I want to only flood to people who have a unique 2-hop neighborhood. Well, in this case, I'm going to flood to all 4. But what I do is I look at A and I say he can reach these 2, or this blue one, and I say the orange one can reach these 2, et cetera, right? So what I do is I pick a set of reflooders that will minimize the number of neighbors that I need to flood to. In this case, it's still all 4, just because I have 4 sets of neighbors. Now, when I move from this blue router down to this side, however, what I look at is I say, all right, I have 2 neighbors that can reach the same 3rd hop or 2nd hop right here. So I flood to one normally, allowing him to reflood. And then I flood to this 2nd one in a way that does not allow him to reflood. What I do is I use a link local flooding mechanism. Now I'm going to show you this on a flow fabric. I'm going to back up in the topology to make sure that you understand. This is much less efficient on a butterfly as I'm showing it as it is on a flow fabric. But still, it does make a huge difference. So this is my forwarding optimization. I take my 2-hop neighborhood, my neighbor's neighbors, I figure out what's the minimal set of neighbors I can flood to that will allow me to reach everybody in the 2-hop neighborhood. And then I simply only flood to those that I need to. So this is local distribution. I do that using a very specialized form of SPF. It's not really that specialized. All I do is I set on my link cost to 1, run SPF, and figure out what my 2-hop neighborhood is. And then I figure out the minimal set of intermediate nodes that can reach everybody in my 2-hop neighborhood. It's very, very simple. And it's just a single SPF run for every change. In the reverse direction, let's say that this router right here has received the LSP update from this network going away. When it receives that update, say it receives it from this router right here. When it receives that update, its natural inclination is to reflood back. But what the reverse optimization does is it says, don't reflood back along your shortest path tree to the source of the change. Now, this is where destinations and nodes in the tree make a big difference. Because the origin of the change is this node, not the destination itself. So every one of these routers will receive 1 copy and will refuse to flood it back to their alternate. When this router receives a copy, well, he's not going to receive a copy, but anyway, because it won't be reflooded back. But say that everywhere in this path, you're going to not reflood back. This, in my little test network, reduced the number of floods or LSPs received by any particular router from 40 to about 4. So it's about a 10-to-1 reduction. Now, in a real flow fabric, rather than in a butterfly, if you look at this, say the change is right here. Flood here, none of these need to be reflooded. This refloods. All of these guys see that all of these routers in the spine are on their shortest path back. All of these see that these routers in the spine are in their shortest path back. I get precisely 1 copy of the LSP to every intermediate system or every router in the network. What happens if I drop an LSP between these 2 routers? Since I only have reflooding on, this router is not going to receive it because he's not going to receive it from the alternate path. Well, that's okay, because in ISIS, I have this concept of a CSNP. And in just a second after the flood, I'm going to send it CSNP, and it's going to say, this is what my database looks like. If your database doesn't match, you need to ask me using a partial sequence number packet or a PSNP what I've missed. So it is reliable flooding. Okay, so implementations of this are, if there's a daemon in FR routing called Fabric D that you can compile today and test if you want a containerized version to play with. By the way, there's also a containerized version of Rift if you want to play with it. You have to email me or Tony P, and I'll see if I can find a way to get you in touch with Tony P to get a copy of that. It's a precompiled executable. It's not open source. So you can actually see the source code in FR routing for implementing Fabric D. There is an experimental implementation in Juniper. Can't believe I misspelled that. These are the same basic principles implemented in OSPF. There's a lot of small scale tests to verify the principles. There's this one large scale virtual test bed I've talked about. And Shraddha, who is doing the implementation in the Juniper implementation, is working with me on a lot of new optimizations to local flooding. All right, so this is the very big slide that just kind of compares BGP to IS modified for DC fabrics using desktop flood to Rift. So you can just go through this yourself and think about it. I didn't give you the slides, but this just kind of gives you a sense of where things are between these different technologies. So that is my last slide. I don't know if we have any questions. I'm not paying attention to the chat window, but I'll leave that up there. Sorry. My screen share just died, didn't it? Darn it.
One question is, where do you see work like LSVR going?
Where do I see? I'm sorry, which what?
LSVR. Means
Oh,
like
LSP. Yeah, so I hope it doesn't go anywhere. So LSVR is problematic from my perspective. I understand the point behind trying to scale the way things are being scaled and stuff, but I worry that LSVR is kind of trying to, I don't know how to explain it. It's trying to solve problems that I'm not sure exist. They're trying to use BGP's flooding semantics with ISIS's and OSPF's shortest path first semantics to create a new protocol. And I'm not really crazy about that whole idea. So that's kind of my opinion about LSPR.
So the entire BGP work in the data center was triggered by RFC 1738, right? So that's what started the whole thing with the experimentation of BGP in the large scale data centers.
Right.
But now you are finding, so the arguments you are advancing for link state, you're saying applies to the same large scale data center networks. Right?
That's correct. Yep, that's correct. So the way I would put it is ISIs modified for data center fabrics would be good up to the scales I've talked about, 2,500, 2,600 routers, a couple of 100,000 routes. If you get much larger than that, you probably want to look at something like Rift, but there's no reason you couldn't scale Rift to say 1 million routes or, 10, 15,000 nodes or even larger and still get really good convergence time out of it.
Okay. We'll go through your slides.
I can send you a copy of my slides.
Yeah, Russ, that would be really helpful. It would be nice to.
Yeah, I mean, the problem with my slides is they don't really say anything.
Yes. Good thing is that we have the recording as well, so.
Right, exactly.
And your draft seems to have expired. Are you going to put out one more?
Oh, has it? I'll look. It's not supposed to be expiring.
Yeah, it says April 2020.
Okay, no, I'll push a new one. I didn't know that it expired. Yeah, I'll push a new one out. Not a big deal. Shraddha and I are still actively working on it. So, yeah, we'll push a new one out.
Thank you for an interesting talk.
Yep, thank you for inviting me.
Russ, one last question. In the ITF, how do you see this progressing with all these multiple solutions? What do you think is the future? Is it going to be like everybody going their way, and since it's data center, maybe the interop thing is also kind of limited, and maybe multiple solutions can actually exist. It's not really a service provider network. So is that what is happening in ITF, that let's make working group for everything, and within the LSR as well, having multiple solution? Is that the reason?
Yep, that's exactly what's going on. I've actually talked to the ADs about this and made a very strong case that we should allow all these to work forward because there's no interoperability issues. So that's the path the ITF is taking right now, is that let 1,000 flowers bloom. Let's see what happens.
Yeah,
we'll just let it go. Yep, thanks.
Thanks, Russ. Okay, so next, any questions? Last questions? We have 1 minute. Okay, let's move on.
And feel free to shoot me questions in email or PM on LinkedIn.
Thank you, Russ. Okay, next. we have Gurshabad with a very interesting talk on how India censors the web. Gurshabad is from the Center of Internet and Society, CIS, and in fact, he has been involved with RFCs We Love in the past. We have had one of our meetups at the CIS as well. So thanks to have Gurshabad back at RFCs We Love. This is the paper that he presented in HRPC research group at the last ITF as well. So this was really interesting. So we invited him to talk about this during the our meetup as well. Gurshabad manages the legal and technical research in freedom of expression team at CIS, and he is focusing both at the constitutional law regulation and the network security side. So welcome, Gurshabad. Go ahead and share your screen.
Thank you so much. Yeah, I'll. Great.
Are you seeing a present now at the bottom left?
Yeah.
Bottom right, sorry. Yes,
yeah, can you see the slides?
Coming. Yep.
Perfect. Maybe I'll. Okay. Still working? I'm full screen now. Yeah?
Working. Go ahead.
Perfect. Yes. So in this presentation, I'm going to present a paper that I wrote with my colleagues Kushagra Singh and Varun Bansal. And just to shout out to Akash for helping design some of the slides. There'll be like a video explainer on the paper soon as well. So just a brief background, and I'm sure like people, especially those of us who are living in India, have seen a website blocking notice which says something like, hey, this website is blocked on the orders of the Department of Telecom or something like that. So quickly on the legal background, basically there are two provisions in our Information Technology Act that allow governments and courts to pass orders to ISPs to block certain websites. And the sort of a disclaimer as we go into this, as this in our sort of legal research, we found that Indian law actually doesn't prohibit accessing any blocked website. So that's why we were able to do what I'm going to describe in the presentation. If you've experienced this, then you might have seen a censorship notice like this sometime. And through anecdotal evidence, through news reports, we know that what we found is that websites were getting blocked randomly in India. And so people would one day just complain, oh, Reddit is inaccessible, Telegram is inaccessible. And if you've been following the news recently, the Department of Telecom told ISPs to block WeTransfer, which is this sort of file sharing platform. And if you go to this news article from April 2019, that talks about Reddit and Telegram being inaccessible for certain users, we'll find 2-3 very interesting things, which is first, if we skip to a particular paragraph, this talks about that so there's this website called indianqanun.org, and what this website does is have basically all court orders archived online for public access. And Reliance Jio, which is the most popular internet service provider in India now, Jio's users were complaining that the site that they were unable to access indianqanun.org. And so Sushant Sinha, the article gets the name wrong. Sushant Sinha, who's the co-founder, he contacted Reliance Jio, and Reliance Jio told him, we received a blocking order from the Department of Telecommunications, and they rescinded it the same day. And basically, this tells us that the experiences of web censorship and website blocking in India can be very arbitrary. But interestingly, when they filed a right to information request with the Department of Telecom, the department got back and said, "Oh, we didn't issue any order." So this tells us 2-3 things: that internet service providers may be blocking websites arbitrarily, and there doesn't exist enough empirical evidence to sort of hold these ISPs accountable. And also, if they are blocking websites arbitrarily, then it's in clear violation of the net neutrality regulations that we have since 2018 now. So there are other stories, dowrycalculator.com, which is a satirical website on the practice of dowry. But so sort of these anecdotal evidence, and there's just thousands of websites blocked in India. I'll get to that in a second. The research questions we got motivated to study were what methods are ISPs using to block websites, and are all ISPs blocking the same websites? So there is, related previous work on mapping and measuring web censorship. Largely, the studies have focused on countries like China, Pakistan, China, Iran, I think, which I've seen the most studies about. But those countries have very centralized mechanisms for web censorship, in that China, for example, has made its network architecture so that almost all traffic will flow through nodes, what are collectively referred to as the sort of Great Firewall of China. And Iran, for example, there's this huge AS through which almost all traffic passes, and that's how they enforce their web censorship. You have monitoring tools such as Uni and Sensor Planet, which are also doing great work on measuring this. So we build upon the methodologies that have been developed in previous studies and these tools, and we sort of improve ways to detect when an ISP is blocking a website, and that's what I'll talk about here. In India, there is another paper that studied web censorship in 2018. But the second research question that I talked about, which is, are all ISPs blocking the same websites? Which is a large policy question as well, as it relates to net neutrality, which I just talked about. So this hasn't been studied at a large enough scale. And also, we found that their work needed updating, because we were getting different results than they were in 2018. So very quickly, what we did is we just a note on like website blocking orders in general. If the government passes an order, especially under one of the provisions I talked about, which is Section 69A of the IT Act, then these orders are not available for the public. They are not published anywhere. And in fact, there is a clause in the regulations that requires internet service providers to maintain confidentiality of these orders. So there's no quick way to get access to those. Sometimes they do get leaked to the press, and so what we did here is we collected all publicly available government orders, or publicly available leaked orders in that sense, and court orders, which are usually in the public domain. And we also collected user reports, especially the ones collected by the Internet Freedom Foundation. And by that, I just mean users reporting that I am unable to access this website, or traffic from that server. So that was around like 10,000 URLs, and after removing duplicates. And for our analysis, we're just focusing on blocked websites. So we strip the URL of the any resource, and we're just checking for essentially domain names now and host names. So at the end, we arrived at this list of like almost 4,500 blocked websites, potentially blocked websites in India, I should say, because some of them may not be blocked. And as far as we know, this is like the largest known set that has been collected till now. And what we do is we're in Bangalore, and we ran these tests from 6 different ISPs here: ACT, Airtel, BSNL, Jio, MTNL, and Vodafone, which some of you might be currently using as well. Like together, these serve around 99% of internet subscribers in India. So this is the latest data from the Telecom Regulatory Authority of India. So the large set of potentially blocked websites and the ISPs we're testing from should give us a fairly nice idea of how ISPs are blocking websites in India and which websites are blocked. So very quickly, DNS is the service that gets you the IP address for a host name, and this is one popular technique used by ISPs to block websites. So usually your ISP configured DNS will give you the right response if it doesn't want to censor a website. But what it can do is poison its own record and basically send you a different IP address than what is set by the site maintainer. And this IP address, if you request it, it might be set up to, let's say, serve you a censorship notice that this website is blocked. The other thing they do is that since most DNS queries are in plain text still, I know in previous RFCsWeLove sessions we've talked about DNS over HTTPS and DNS over TLS, but if you're using vanilla classic DNS, then even if you try to contact any other DNS server, what the ISP can do is like have a middle box somewhere that intercepts this and sends you a bogus IP instead. Now, how do we detect censorship through this? And there has been previous work in this. Basically, the crux of this is that you compare what you see as the response from the ISP to a DNS server's response, which you know to be not censoring requests, right? So let's say you can set up a Tor circuit that ends in the US and you get a response from there, and US largely doesn't block domain names. Or you can use something like Google's or Cloudflare's DNS over HTTPS server. The problem with this is that these resolvers can return a different IP address for legitimate reasons, which is for load balancing reasons or to get you a server that's closer to you. So there's a paper by Lau et al. Where they select multiple control resolvers and they only investigate where you receive an IP which is the same as you might have received from the other resolvers. The problem with this is that it significantly reduces the size of the test list because there is a legitimate reason you might receive different IP addresses. So, and the Indian study I talked about, what it does is that what it says is if you receive an IP address that belongs to the same AS as the ISP you are on, then they are censoring the website. The problem with this is, at least theoretically, do we know that the spoofed IP address will always belong to the same AS? Technically speaking, they could send you an IP address which is belonging to another AS. And second, what if the website is hosted on the same AS? So you wouldn't be able to detect DNS censorship in these cases, or you will be marking stuff as being censored when it's not. So what we do is we query 5 trusted, that is like non-censorious resolvers, and if the response we receive from our own ISP's resolver, if it is from the responses, if it is already in the response, like the IP address is already something we've seen in our control servers, then we can mark it as not censored. If we receive a response that is NX domain, which is like doesn't exist, or a bogon IP, then we mark it as censored. Otherwise, what we do is we collect all the IP addresses that we received for our large set of potentially blocked websites. And if there is an IP address that is present with an unusually high frequency, this sort of relies on the fact that we know for sure that most of the websites in our list of potentially blocked websites are blocked. So what we do is compare the relative frequency of the most subsequent IP addresses in this set. And if you find such an IP exists, then you know that's the one they're directing to. And for each website we notice that IP, we mark it as censored. So that's DNS is one method ISPs are using to block websites, and they can use to block websites. So that's the methodology for that. Next is HTTP, our favorite web.
Yes. If I'm
Subhijit,
sorry.
just 1 second.
Yeah.
Subhijit Day, I think you have pressed on the button presenting. Could you stop that? Otherwise, I have to remove you because you have you have started presenting, and Gurshabat presentation is gone. Okay, I think I need to maybe remove him. 1 second, just give me a... Okay, I've removed him. And Gurshabat, can you present again? So that your screen is visible. Present now.
Yeah, it actually says
you're presenting.
I should be sharing. Yeah, can you see
it? Maybe stop and start again. That usually works much better.
Yeah, 1 second. Okay, working now?
Yes, go ahead. Sorry for the interruption.
No, no problem at all. Yes, so the second method ISPs can use to block websites is the fact that if you're using plain text HTTP, not all websites are using HTTPS, and sometimes your browser will make a plain text HTTP request first before it is redirected to the HTTPS website. So the host name will be in plain text, and usually what will happen is if the site is uncensored, then you're able to get the web page normally. But if the ISP wants to block it, what it does is like reads the host name present in your HTTP request and sends you back a censorship notice instead. So it doesn't let the connection go through to the host. Now, there's again previous work in the area that tries to detect HTTP censorship. It's a bit tricky because unlike so while there were problems with comparing responses from control servers in the DNS methods, there are sort of the similar problems here, which is that if I query for the same website in the US, I might actually receive a different version of the website. So I can't directly sort of compare the responses. But so people have developed a method to sort of compare the length and structure of responses, detect censorship notices, which Jones et al. Did, and UNI, the Open Observatory of Network Interference. They do a very elaborate comparison which relies on status codes, headers, and lengths of the response. So the previous study I mentioned, Yadav et al., which studied web censorship in India, they found lots of false negatives and positives for India. We do a very, I think, minor improvement over UNI's method in this case. Since it's not a great improvement, and I'm already almost at 20 minutes, I'll skip this one, but happy to talk in detail if anyone's curious. We basically try to extract a lot of values from the response, including status codes and lengths and session header keys. But so we arrive at a method which is a little bit better in terms of F1 score, at least, than UNI's method. So the last thing, which basically hasn't been measured in India, whether ISPs are using this method, this is called the server name indication. It's an element, it's an extension to the transport layer security protocol, where essentially if you want to have a server which hosts multiple websites and you want to host multiple HTTPS websites, this extension travels in plain text to tell the server which sort of website you're trying to access. And since you're not connected with the website, it's not something you can encrypt. There's ongoing work in the TLS group to develop encrypted SNI, but SNI is largely what is used now. And so, since it travels in plain text, again, ISPs can have a middle box which detects the name of the website you're trying to access. And here, they can't send you a censorship notice because TLS is supposed to provide you guarantees of authenticity, integrity, and confidentiality. So the maximum, the most they can do is send you a TCP reset, which basically stops your connection. And so there's not a lot of work on detecting SNI censorship. In fact, I think we might have been the first ones to propose this, which is we set up a server that accepts TLS connections, even if it doesn't host the website that you may enter in the SNI. So I can set up a TLS server which just establishes connections, does everything successfully, even if you give me a random SNI. So we specifically use TLS 1.3 because what can happen is that so there is a client hello that goes from you to the server, and there is the server hello in response. Now, the server hello in TLS 1.2 and before that, it used to be in the certificate in the server hello used to be in plain text. Therefore, anyone could see what website you're trying to access. And technically speaking, ISPs could use that information to censor websites. So we use specifically TLS 1.3 to detect only SNI-based censorship, and we establish this connection with our server, and we send the SNI of a potentially blocked website. So if you spot a failure to connect, we know it's censored. Yes. So quickly, I mean, after running all these tests from on the ISPs I mentioned, these are the results we got. That since the government is not mandating any specific method to use for blocking websites, ISPs are using whatever they want essentially. And in fact, some ISPs are using multiple methods. And for example, if you zoom into ACT for a second, they are blocking 233 websites in our list with only DNS, around 2000 with only HTTP, and both to around 1600 websites. So it's a wild game out there. So anything is happening. In fact, even in a single ISP, you would see different websites being blocked by different methods. And for the ISPs in which we saw multiple methods, this is the thing. I mean, there were three: ACT, Airtel, and Jio. So from the methods we covered, 4 ISPs are using DNS-based censorship. Most are sending censorship notice except Airtel, which is sending you an NX domain, in which case you'll just see not found, like a not found error in your browser. And we didn't find any instances of collateral censorship. So collateral censorship is when even if you are on ISP number 1, let's say, you experience censorship because of the practices of another ISP, because let's say your traffic might be traveling through their network as well. So we didn't observe any collateral censorship here. 3 ISPs are using HTTP-based censorship. And again, Airtel is not serving censorship notices for some reason. They're just sending a TCP reset. And we observed some collateral censorship in this case. Now, when it comes to SNI, as I said, this hadn't been recorded in the Indian context before. And what we found is that Reliance Jio was using SNI-based blocking. And as I said, censorship notices are not possible in this technique at all. What we found in terms of the second research question I talked about, which is, are all ISPs blocking the same websites? We find that the answer is a clear no. In fact, so from our list, if you take out the 4033 websites that are blocked by at least one ISP, you find that, let's say, for instance, Airtel is blocking almost double the number of sites that Airtel is blocking, right? And yeah, the numbers are here. And interestingly, only around 27% of the websites are blocked by all 6 ISPs. So clearly something is going wrong in terms of them not complying or blocking websites arbitrarily, perhaps. And similarly, on like the opposite end of the spectrum, we found that 215 websites were such that they were blocked by only a single ISP of the 6 we tested in. And this is just a comparison of block lists across ISPs. And so here, the smaller the circle, the less overlap there is between the lists. This is just the sort of intersection by union of the different block lists on each ISP. Yes, as I said, there are only 2 things you can conclude from this, which is ISPs are either not complying with government or court orders, or sometimes what happens is the government will say stop blocking this website, or the courts will say block this website for 2 weeks since we're waiting to hear from another party, or in cases like that. So either they're not complying with the website blocking orders, or they're not complying with the subsequent unblocking orders, or what they're doing is arbitrarily blocking websites without any legal order that comes to them. And if it is the second case, then, or if it's the first case, I should say, in any case, I think the evidence that we found is suggesting that they're not following net neutrality regulations to the in spirit or word here. So the other thing, I mean, I haven't talked about the legal and policy angle to this. In fact, the website blocking regime in India has been challenged in the Supreme Court. There are still ongoing challenges in the Delhi High Court, for instance, because of the opaque way in which these orders are passed to ISPs. ISPs are not allowed to tell anyone. And so we come into this problem with already that large background of having a need to reevaluate the legal provisions that enable this sort of censorship. But clearly what this also asks for is that we should have a net neutrality monitoring mechanism in place. So regulations are not just enough. You need a TRAI or some other body to set up to actually monitor whether ISPs are complying with the regulations. And the third thing is that if they are blocking a website, we deserve to know. And as we saw, Airtel is not serving censorship notices to its users. And if you use SNI-based blocking, for instance, then you are unable to serve a censorship notice. So these are some other concerns from a user's perspective and their experience of web censorship. Yeah, and I'll end here. I think the last thing is that we've collected these readings from a single location, and there are disadvantages to this approach, which is that middle boxes may not have been installed uniformly across all regions. So in fact, that makes the case worse for ISPs, in my opinion. But the next thing we're working on is we've developed a mobile application that will basically allow us to distribute these tests and allow people to help us map web censorship in India and build a stronger case for why we need legal reform and both a net neutrality monitoring mechanism. Yes, thank you so much. I love discussion or questions, if any.
Folks, anyone has any question?
Yes, Dhruv, can I ask one?
Yeah, go ahead.
Thanks, Gushabat, for the nice presentation. I just wanted to know what was the time frame of this particular study? I mean, was it running across 4 weeks or maybe a months? I mean, how was the time duration?
Yes, so for this particular sort of set of tests, we only ran it in a duration of a week, and this relies on those readings. But So this is again a very good point, and I'll because ISPs can keep changing their censorship mechanisms, and because of the number of blocking orders, it can so happen that certain websites become blocked or unblocked over time. In fact, after we published this, we heard reports that Airtel was also using SNI blocking, and we have after this after the publication of the paper, like confirmed that independently. So I think that's why the sort of future work I referred to is very important, because we need readings from across geographies in India and across time to get a better idea of both the research questions, in my opinion.
Okay, thanks a lot. Thank you.
Gushwa, there's one question for you on the chat window, which is there any evidence for DNS injections attack as a censorship technique?
So, great question. I think in the method we devised, there was no need for us to distinguish between DNS poisoning or DNS injection. So our test only, let's say, if the ISP is using either poisoning or injection, we call it DNS tampering. So we've only detected evidence of this. That's what our test was devised to detect. My intuition is that most ISPs are actually doing DNS poisoning and not injection. But I don't have the data to sort of prove that right now. But there are ways to detect, like sort of distinguish between these two methods.
We have a couple of more questions, but we are actually over time. So I would like to move on to the next presentation so that we can keep it. But guys,
I'll respond in the chat.
Yeah, go ahead and respond in the chat so that that others can also look while we start with the rest presentation. Could you stop sharing?
Done. Thanks so much.
Thank you. Okay, so next we have our last presentation, which is decreasing access time to root servers by running one on the loopback. This is described in RFC 7706. And the next speaker is Swapnil Pattekar from Shrestha IT Technologies. He's a network engineer and a researcher with interest in DNS, DNSSEC, BGP, etc. And he has given us a nice introduction to DNS and DNSSEC in the last RFCsWeLove as well. So we are happy to have him back and continue the discussion here. So Swapnil, off to you.
Thanks, Dhruv. Okay, just give me a minute. Dhruv, can you confirm if you're able to see the presentation?
Yes, I am. Go ahead.
How about it now? Is it full screen?
Yes.
Okay, great. Super. Thank you. So I'll just skip the introduction slide for that matter. And I have already shared the presentation PDF with Dhruv. So I think he will put it on the blog, the ISOC blog. So you can always access it from there and learn about what other things that I'm usually up to. Okay, so current state of DNS. So when I say DNS, I'm talking about root servers more specifically. So there are a few problems with regards to the root servers in general, and I'm probably going to summarize to a very few set of problems so that I can then point to a solution, which is RFC 7706. So one of the ever challenging problem with respect to root servers is access to the root servers, and this is dependent on a couple of different factors. One of the factors is the element where the root server is located inside the country. So say, for example, in India, we have a lot of root server instances, right? Similar to other countries will also have or may not have instances of the root server. And the second element is more specifically with to do with routing. And I'll come to that specific point probably in the next couple of slides. The other issue with respect to the root server is, so although we have DOT, that is DNS over TLS, as well as DOH, which is DNS over HTTPS, what these two technologies are typically doing is they are encrypting the traffic between the client and the recursive resolver, right? They're not encrypting or securing the entire communication. So at this point of time, the communication between the recursive resolver and the root servers is purely unencrypted. That is, it's completely in the open. The other element is resiliency. So when I talk about resiliency, as you already know, there are 13 root servers in total, but the number is quite large when we take the anycasted Anycast model, which uses 1084 instances all around the world. So the question is, how do we, the broader question that I'm posing with respect to this presentation for today is, how do we increase the resiliency against something like a denial of service attack or a distributed denial of service attack on the root server system? And if I have to point out to one of the use cases or one of the examples for DDoS would be the attack on Dyn infrastructure, something in probably in 2016. So you can actually look that up and because the infrastructure that Dyn was typically running was also in an Anycast model for that matter. And on a broader note, since the root server infrastructure doesn't penalize abuse, should we continue abusing it? Now, again, this I'll go into more detail with regards to this probably in the next couple of slides. So sometime in April 2020, the ICANN or the ICANN IMRS instance, which stands for ICANN Managed Root Server Instance. So the people from the Octo team, that is Office of the CTO, which reports directly to the which is under ICANN, did a study sometime back in April 2020, where they looked at specific instances of the root server, and these were primarily somewhere in France. So they concentrated the entire study on looking at traffic with regards to the froot. So if you do not know about this, ICANN runs the froot root server for that matter, and they looked at some specific, I believe, a few number of instances in France, because the reason why they did this is France went into lockdown pretty early, and so they wanted to focus on that area to begin with. So one of the very interesting findings from that study was the number of queries that were hitting the root servers, and this became more apparent because a lot of people started working from home. So even though they were, prior to COVID, a lot of people working in, let's say, in companies and organizations, there would be a recursive resolver, which is basically caching a lot of information. But when after COVID, after the lockdown started coming in place, a lot of users, using internet infrastructure from home, and the number of queries to the root increased. That is something that they found out. Now, apart from that, they also found out something very interesting, and this is something that is not new, but probably from a volume or a quantum perspective with respect to number of queries is a bit alarming. So what they did find out was the number of queries from I think I need to change it. It's not from Google Chromium account. It's from Google Chromium, browsers or browsers which are using Google Chromium for that matter. So my apologies for that. So queries for non-existent TLDs, right, from Chromium-based browsers comprised of 1/3 of total queries to the IMRS, which is ICANN Managed Root Server. And that's huge, because when you compare the number of queries in general, I would probably phrase this as junk queries to the root, right? So significant increase in queries for other non-existent domains in the other TLDs like .corp, .local, .home. So just to give you an idea a bit, these are non-existent TLDs. These are used primarily by various I would call it a software or operating system. So Windows uses, if I'm not mistaken, .corp. It sends a lot of queries for .corp, primarily to look into the corporate DNS infrastructure for that matter. .home is also, I believe, used by Windows operating system in some specific use case. Before I move on, I wanted to also summarize. if you do not know about this, so what typically happens when you load Google Chrome or Chromium-based browsers is at startup, it sends 3 queries, which are non-existent queries. Basically, I would call them as a string between 7 to 15 characters to ideally find out if there is a captive portal in the network. So it sends 3 queries, 7 to 15 characters in total to primarily check if there is a captive portal. So ideally what it does is once it sends the queries, if there is a recursive resolver or typically a captive portal in the network intercepting the traffic, if it responds to it with a valid answer with an IP address of the captive portal, Google Chrome would ideally, or Chromium-based browsers ideally understand that there is a captive portal in between, and you would ideally see the login page or the captive portal page for that matter. So if you want to look into more details about this study or this paper, I would suggest you look at the analysis of the effects of COVID-19 related lockdowns on IMRS traffic. I have a link for the study at the very end of the presentation, so you can actually look into that. Now I come back to the earlier point which I talk about, where I said that access to the root is dependent on 2 things. One is root server instances located inside the country, and the second is routing per se. So here is something that I will probably talk about. So what you're seeing on this specific slide, especially the image, is basically a trace route which is from AS9498, which is Airtel, to the iRoot server. So iRoot server is managed by the root server operator is NetNod, and they run a Anycast node, which is IPv4 node in a Mumbai data center for that matter. So if you look at the trace route, by the way, I'm actually so this screen or rather this image representation is by using something called as the RIPE Atlas system. So I typically used the RIPE Atlas project to run trace routes from different locations in the country to figure out whether the traffic towards iRoot is actually going to within India or whether it is using the transit path. So if you look at the trace route, you can typically see that the traffic is going from Marseille to Frankfurt and then to probably to NetNod. So as you can rightly see, this traffic is not going to the local instance of the root server here in India, but rather it is going to somewhere transiting outside of India for that matter. Here is another example. Now let me be very transparent about this. I don't mean to be picky about choosing AS9498, but that is one of the examples that I could think of when I was looking at doing a study on something like this. So here is another trace route from again AS9498, which is Airtel, to the K-root server. So the K-root server is managed by the RIPE NCC, which is the DNS root server operator. They are also the RIR, that is Routing Regional Registry for the European and Middle Eastern region, if I'm not mistaken. So they run an Anycast node in Mumbai as well as in Noida, both IPv6. And again, you can see that from the trace route, you can figure out that traffic is again transiting outside of India. So the point I'm trying to make is, even though there are root server instances within India, due to not efficient routing per se, the effective path is not being taken, and primarily that is the reason why traffic towards these instances is going outside of India. That's where that's where we have something called as RFCsWeLove, which stands for decreasing access time to root servers by running one on the loopback. So the specification ideally talks about, so this is more of an informational specification at this point of time, but based on what I've seen on the activity on the RFC editor as well as other network operator groups, I can see that this specification is being probably being focused upon in a lot of ways to solve a number of problems in the DNS infrastructure per se. So one of the objectives of RFC 7706 is to have an option where it gives an option to the DNS resolver operator to prevent snooping of requests, because ideally what would happen is the requests from the DNS resolvers per se will not move outside the resolver network architecture primarily. So they would typically be served, from the loopback, and I'll come to that in a minute. The other is decrease the access time, that is round trip time to the root server. So the previous problem which I talked about, where although we have root server instances within India, when we access those root servers, our packets are going transiting outside of India. Faster negative responses to the sub-resolvers, and this is again something very useful when we talk about the earlier use case where Chromium-based browsers abusing the root server system by sending huge number of every time Chrome or Chromium-based browsers start or boot, they are sending 3 queries which are non-existent to the root server system. So eliminate junk to the root. Ideally, increase the resiliency of the root server system. As well as reduce the attack surface, primarily because less number of transactions by using something like this on the resolver, less number of transactions would reach the root server, Anycast system for that matter. And privacy, hide queries to the root. So from an implementation perspective, what it implies is ideally running on the existing recursive resolver, there is an opportunity or there is an option to run a root zone, primarily have an instance of the root zone which is only running on the loopback, and this is typically or more specifically on the recursive resolver for that matter. So recursive resolver, instead of using the actual root which is on the internet, will ideally use the one which is running on the loopback. The other advantage, or more specifically what the RFC typically stresses on, is the communication between the recursive resolver and the upstream root running on the loopback is there is validation with respect to by using something called as DNSSEC. So even the communication between the recursive resolver and the upstream root server, or the root for that matter, is being validated for integrity purposes. So here is a list of DNS root servers which support something called as AXFR, which is basically zone transfers, and so not all. So even though there are 13 root servers A to M, not all root servers typically support AXFR by default, and neither is there specification which says that this, and when I'm talking about supporting AXFR, I'm talking about the root zone. So you typically see at the very top in the subject, I have a specific dot which is basically implying that it is the root zone. So here are the root servers which support this. Again, the earlier point I was trying to make is there is no specification which says that these root servers have to primarily provide this as a service to anyone for that matter. So it might so happen that one of the root server operators decides to disable AXFR on the root zone, right? Here is how you can do this manually. So if you want to actually test this out, you can do something like a dig query on the command line using AXFR on the root zone. So the dot specifies the root zone, and specify the root server which I have mentioned in the previous slide, and you will see that you will get a full copy of the root zone, right? But having said that, there are other problems with regards to this, because there are other the Anycast instances might be serving it differently, so they might not work in a very precise sense for that matter. Interestingly, bind the open source software from ISC. If you install the latest version 9.16.3, you will see in the named.conf there is it's basically something which is commented. So if you see the comment which is starting from slave the following zones till the very end, that is the implementation that I'm talking about, that is RFC7706. So ideally it talks about same things which I've just outlined here, and it mentions that you can slave the root zone, right? So this is something that is built into bind by default if you're using 9.16.3. Of course, different versions provided by the operating system might do it differently, but this is something that I just checked sometime last night on FreeBSD, and this has this slaving on the root zone by default. So here is an interesting project which I would like to point you to. So one is you could do it manually. The other option is to probably slave put the root zone as a slave inside bind for that matter. But there might be certain limitations because recursive resolver operators might not be able to upgrade to the latest version of 9 of bind, or might be using different recursive resolver like Power DNS or Unbound for that matter. So it might be a little difficult to do. So here is an interesting project which is called as local root. It's like RFC 7706, but it is not equal to, because it is just not limited to what RFC 7706 specifies. There are a lot of other things what it also does. So the project is by Wes Hardiker. He's from the University of Southern California. So the ideal logic is the same. Load the root zone into the resolver, so that whatever queries are being made by the recursive resolver, they will all be local, and speeding up response, validation between the recursive resolver and the upstream root that is running on the loopback. And the other advantage with this project is the transfer is using something called as TSIG. So signatures are typically used for transferring the root zone from the local root project, and there are configurations for running this for bind, unbound, NSD, and so on. Right. So let's run a root server for home. I didn't want to take a chance by showing you a demo, because I didn't want the demo gods not to be with me. So what I've ideally done in that case is I have some screenshots which I will probably show in the next few slides, and maybe you can get an idea about it. So the project is available on localroot.isi.edu. So you just go on this specific website and sign up. So there is a register button there. So once you sign up, what you have to do is you have to typically create a TSIG key. So once you create a TSIG key, you ideally can see that, and the web interface does this for you. So you don't need to do anything on the command line. So you follow the procedure which is on the web interface or the web application, and it creates a TSIG key for you. Once the TSIG key is created, you specify the server. So you need to have a static IP address for that matter if you are running a recursive resolver. And by the way, make sure that if you're running a recursive resolver which is public facing, make sure that you're not exposing it to recursion from everyone on the internet, and you have access control list which is basically locking down to a specific set of IP addresses from where you are going to query. Coming back to the local root, so ideally you specify the IP address of your DNS server, select the TSIG key, and once you do that, what it does is it basically spits out a configuration which you can just copy and put it in your recursive resolver for that matter, and you have many options with which you can explore. Now, there are a lot of additional things that this project also includes, and there are a lot of things that the local root project per se is working on. But at this point of time, based on what I know, the public facing application is not yet updated. Hopefully in the next couple of days, or probably in a week or so, you should see probably more features added to the local root. So what can go wrong with regards to the local root project, or more specifically RFC 7706, is if you're a DNS resolver operator, it is one more additional thing that you need to stick into your DNS infrastructure. And ideally speaking, a lot of recursive resolvers tend not to meddle with a lot of things. So this might be something that might typically be a little scary for a lot of folks who are doing it, especially in the production environment. Ideally, I would suggest to do something, set this up in primarily a test environment, which would be a best practice. So I have actually rolled this out for, I would say, medium to large scale network operators here in India. And it's been probably just a few days, maybe a month or so, or around 40 days. So I'm still evaluating the challenges as well as, kind of problems that this brings on the table. Hopefully in the next, maybe sometime down the line, in another couple of months, at the next RFCsWeLove, or maybe in the network operators group meetings, I will present my findings with regards to that. The other thing that you need to keep a lookout for if you're using something like this, if the root zone, so ideally the root zone is basically, in the case of local root, is being is being transferred using tsig. If that transfer fails for some reason, for some amount of time, and there is an expiry time there, then what would happen is your recursive resolver will answer for any queries with NX domain, and which means that internet is typically going to be non-existent for all the people using the recursive resolver. So if you're doing this at home, be very careful. I have something like this running on my recursive resolver at home, and you need to be making sure that you are available 24/7 if something goes wrong. References with regards to the papers that I've mentioned, so you can go ahead and have a look with regards to that. Questions, comments. So before I typically hand over to Dhruv, what I would also like to do is I would like to also mention about DNSOARC. So DNSOARC is basically a non-profit organization, stands for Domain Name System Operations Analysis and Research Center. It's basically a non-profit organization registered in the US. It basically is does a lot of things with regards to so if you're ideally, if I have to just summarize, if you're in the DNS, if you're working on DNS, if you're working on research, if you're doing something in DNS, I would suggest you check out DNSOARC. My company is a member. I would also urge you to become a member of this organization because it provides a lot of value from research and analysis perspective. And there is a link to the brochure, so you can actually look into that. If you have any questions with regards to what maybe how it can benefit you, feel free and reach out to me. And with that, I would, I would like to conclude. Hopefully, I think I was right on time. So if you have any questions, I would love to take those questions. And thanks for the opportunity. Thank you, Dhruv.
Thank you, Swapnil. Any questions, folks? I have one while other folks are thinking. What's the change that they are proposing in 7706 bis?
So what is ideally the change? It's typically not a change per se. It's at this point of time, it's an optional or opt-in kind of a model where ideally right now, if you're running a recursive resolver. So as an example, at home, I'm running a recursive resolver, right? So all my queries typically, or anyone who is using DNS anyone who's accessing internet in my home, all my queries go to a local recursive resolver. And that recursive resolver is directly talking with the root server. So I don't have it configured as a forwarder. So I'm not using public DNS or quad DNS providers like 8.8.8.8 or 9.9.9.9 or 1.1.1.1, right? So I'm running my own recursive resolver. In this case, in this context, say for example, you are doing something like this, or you are a recursive resolver operator like the quad DNS resolvers, or you are a network operator or an internet service provider running a recursive resolver. The issue, as I pointed out, is accessibility or access time, round trip time to the root servers is basically not something which is in control because it's based on routing. It might not take an optimal path. So access time is huge, right? So as I showed you in the couple of slides with respect to the tracer using the IP address measurement, you can see that traffic, even though there are root server instances in India, my traffic typically went out of India to an instance somewhere in Paris and in Sweden for that matter, right? So using something like RFC 7706, what advantage one gets by doing that is, one is faster response time because you are running a copy of the root zone on the loopback of the recursive resolver, right? So I hope that answers your question.
Kanan, go ahead. I think you have a question.
No, I didn't have any question.
Okay.
Interesting presentation. Thanks, Swapnil.
Thank you.
Thanks, Swapnil.
Okay.
So one last slide, and then. Okay, folks. So thank you for attending. The last ask would be just go to menti.com and maybe you can provide us feedback for this and any other future events. And as you provide feedback, feel free to log off. and this feedback would then be part of our proceedings as well. So this would be a good way to please feel free to give any feedback that you have. And thank you everyone for attending.
Thanks, bro, and thanks everyone for attending.
Thank you. But please request to give feedback. That will help us to plan these events much better. Thank you. And have a good weekend. Stay safe. Bye.
Thank you. Bye-bye.